let me share with you the rest of this document. Okay, so the next discussion is called structural systems. I know this name is not really very common to you. Some of you will say, okay, what do you mean by structural system? So in structural engineering, there are so many structural systems that we can use to simply carry the load. I'll give you one name for now, and then the rest will coming shortly. Huh? So beams. So beams, I think all of you guys know what does it mean, beam. It's an element that mainly horizontal, spans between two supports or more, and can simply bridge the load from the floor to the column. So that's called beam. Okay, but the thing is not only beams. There are so many other structural systems that's available for us and for engineers to use. And so this choice that should we frame our roof or floor with beams or other structural system, it's kind of not really easy discussion. And simply are so many factors. You see them listed on my screen. One which is very obvious, very obvious, which is the allowed spacing between the supporting elements, and I say columns. So the spacing between the columns is one or main factor that dictates the structural system. Okay, it's kind of a very well-known people. They are building with those systems for more than 100 years. So we know, the economical choice. If the spacing between the column is 10 feet, like for example in houses, normal houses, the spacing between 10 to 15 feet. So we know right away. We know that it's a beam. And that's what we do. But I want to take you to the other end, which is what if the spacing between the column is 30 meter or 40 meter? Guys, you've been in SAIT, you've been to I guess every time you go outside from the SAIT train or you come back, on your side there is I think the basketball, like I think the arena, right? So do you see any columns in the middle? Can we add any columns in the middle? Can I get some answer? Can we?
No.
No, you cannot. And the reason why you cannot, because simply it's contradict with the function of this hole. So which means we cannot. Can we use beams to simply bridge and simply carry the roof? Of course we can. Nobody can say no. You can make beams, but the problem is this beam will be as big as the bridge girder. Completely inefficient, completely uneconomical, which means don't use it. So what's the other option? Can anybody tell me anybody was in this arena or close to it and look at the roof of it and see what is the structural system? What do we call it? I know that you guys know this name. Any help?
Open web steel joists or rafters.
Oh, thank you so much. So here we go. So OWSJ, which is open steel joist. And to be honest, like in industry, we don't call it the OWSG. I know that they have the same name, but we call it truss. Okay, and I know this OWSJ. I know it's a very common name, but we typically do it for not those big members like the HSS, and so in general those are called truss. Okay, truss elements. Okay, so here we go. So we have now two names. We have beams. We have trusses. And I'm going to talk about trusses later on, and you guys know about trusses from your static course, okay? But now we get to know what do we mean by structural system, okay? Number two on the list is the applied loads. Sometimes the loads are very light, and sometimes the load are very heavy loads. So the applied load is another factor. Number three is the allowable deformation. Are we allowed to have a deformation of 2 millimeters or 5 millimeters, or we can accept a way bigger deformation? So this is something also, it's a factor when we choose. Some systems, they are fantastic. Their deformation is so little. I'll show you which one is so little. and some other structural system, they deform so much. For example, look at if you have a suspension bridge that has cables. Those cables, they deflect so much, which is sometimes okay, but sometimes is not okay. For example, if you have a railway, the railway, like if you have a train going on top of of a bridge, then in this case, if you allow lots of deformation for a railway, doesn't work. You will bend and it doesn't work. So you have to make sure you control also the amount of deformation. The availability of the analysis tools and engineering experience. Okay, so how many of you have seen a cable stay bridge or suspension bridge? Any help? Like in Calgary here, do we have any suspension bridge? You know what that means, suspension bridge? It's a bridge that has big column, big pylon, and there are some, kind of big wires, big cables coming from the, from this column or pylon, and so to hold up the bridge. Anybody has seen anyone in Calgary? Hello, I need some help, guys. You need to talk to me. You guys are looking for the chat. Remember, subjects, I don't see the chat. I don't see the chat. If I ask you to talk, because I'm not looking at the chat. So I mean, you say it, Brody. You say Golden Gate. I'm not sure Golden Gate is. I don't know where is that, but it's not in Calgary. The other one, it's in Vancouver.
It's in San Francisco. It's not Calgary, but it's like the Lions Gate in Vancouver.
Yeah, the one in Vancouver, I've seen it. I have, I went on it for probably 2 or 3 times. It's amazing. I love it. But in Calgary, no, because those are very, very complicated, not only to design, but also to build. Very complicated, requires a high experience. And, unfortunately, we don't use them in Calgary here. Okay. Not very common. So that's why I said here, number 4 is the availability of the analysis tool and engineering experience. Building configuration. So sometimes my windows and doors simply they say, okay, don't do that, do that. Next is skilled labor, which is again same as the cable stayed bridges or suspension bridges. Those are not like concrete guys. You guys, concrete guys, it's kind of easy, just people easy, no much experience. They move the concrete. Probably the finisher is the one who has the most experience. Other than that, it's just normal labor. But for suspension bridge, there is lots of technicality. Those, they are pre-tensioned and it's very complicated. And so that's why not very popular. You need lots of experience. And then finally, sometimes, you have something and you want to make a feature. There are some beautiful bridges, which is very difficult to build. Probably at some point, I'll show you some of those. But there are some bridges, which is, it looks amazing. Some of them, they tilt, swing, they open. Okay, the appearance of the structure sometimes dictates the statical system. Okay, guys. So far I showed you 7 different factors that help the designer or the engineer to pick one structural system, but not the other. Now let's talk about when we say structural system, what do we exactly mean? You can see here I prepared for you guys a list, which is kind of make it very simple. So 1, 2, 3. Number 1 is beam column system, and so beam column system is very simple, and that's what we do for almost every structure that you will see. Very popular, very easy to build, which is here. Look at this picture. Probably I can zoom in so you guys can see. So this picture here is, I know this is a precast, but again, it serves the purpose. So this one here is a beam, and this beam is going on top of some series of column. Okay. Now let me ask you, is that beam simple beam or a continuous beam? Because some beams, they have even the beams, they have subcategory. The beams, they can be simple beam or can be continuous beams. And how do we know if it's simple or continuous? Any help? Again, I don't see your chat, so if you know the answer,
simple beam.
It's a continuous beam.
So here is the trick. Probably I have to tell you which one I'm referring to. You can see here, look at where I'm pointing my cursor. So look at this. What is this one? This one is a joint. It is a joint, okay? Yeah. Simply the joint in the beam, simply it discontinue your beam. And then if this joint is on every column, it means those are simply, all of them are simple beam. If this joint here doesn't exist, it means the beam is continuous on top of the column. Hopefully you guys know the difference between a simple beam and a continuous beam. Okay, next is, before I move to the next part, guys, look at this. Simple beams, do they resist the gravity loads or the lateral loads? And probably this discussion also, we need some introduction. Guys, look at this, look at this. When you look at the loads on the building, it can, some of them, they act vertically, like the gravity, and some of them, they act mainly horizontal, which is like seismic and wind, okay? I'm asking you, if you have a beam, okay, this beam, does it take care of the gravity load or the lateral load? Any help?
You're not sharing anything.
Huh?
Can't see your screen.
I'm sharing with you guys my Outlook, my Microsoft Team meeting. So my picture is simply at the very bottom right. Maybe guys, what you need to do is you need to click on my picture and then pin it. Okay, I can simply stop the sharing, and you just have to pin my picture, right?
Oh, I thought you were showing us a picture, or you're trying to show us something.
No, I'm just using my hand to show you the direction of the load. So again, one more time, the loads, they act in mainly two directions. It's a gravity load from up, down, gravity load, or laterally, left and right. So my question for you is, if you have beams sitting on top of a column, can they take care of the vertical load, the gravity load, or the horizontal load? What do you think?
Gravity load.
Gravity load.
Gravity load, that's correct. So the beams, the way they set horizontally, set on top of columns, they take care of the gravity load only. The beam doesn't do anything for the lateral load, wind, seismic. So now, if this is the case, what do you think, what stops the building from falling down if you have some wind? Any help? If the beam does nothing, for the lateral load, it cannot do anything for the lateral load. So if we have some wind or some seismic earthquake, what stops this building from, tipping over?
Your column.
Brace. You have to brace.
Bracing, yeah, bracing. That's correct. Bracing is one option, but typically in concrete building, we don't do bracing. That's sometimes very rare that in concrete building we do bracing. Very rare. But in general, bracing, we use it in steel. It's very easy to make in steel. Just cross brace and you're good to go. How about concrete? Did you guys know that any element in the concrete building that takes care of the lateral load?
Columns.
Not really. The column is still working on the gravity load only.
The foundation.
Okay, for the sake of time, I'll give you the answer, you think about it, okay? I'll give you the answer, you think about it. What takes care of the lateral load in a concrete building that's built out of beams and column is the shear wall. Shear wall. And exactly what is shear wall in the building? Typically, it's made out of the elevator core or the stairwell. So they make the stairwell walls, they make it as shear walls to resist all the lateral loads, like a stiff element in the building to resist the lateral loads. Okay, now, in most of our building, I can tell you something, that's what we do. We do beams on top of the column to take care of the vertical load, and in the building, we add the shear wall to take care of the horizontal, kind of separated. But sometimes in some building, we are not able to add this shear wall. Sometimes no, sometimes you can't, okay? And then so if you cannot add the shear wall, is there any way that you restrain the building laterally? I know some of you will say, okay, we add bracing, okay? And sometimes even the bracing is not an option. Sometimes, and I'll tell you when. For example, look at aircraft maintenance building. You have a building that we do aircraft, so we enter the aircraft, we do maintenance, okay? You will see for the gate, this has to be open wide. You cannot add any bracing. And if you cannot add any bracing and you cannot add any shear wall, how can you take care of the lateral load? The answer I know is not very easy. That's why I'm going to help you guys just for now. The answer is here. The answer, there's something called moment frames. Moment frames. And the moment frame, it will look like, I'm going to show you the picture of the moment frame. So I'm going to scan here. So this picture here on my screen right now, I'm going to share it with you guys. So I'll share with you my screen. Okay, so here is the picture of a moment frame. And I know some of you will look at this picture and say, okay, Tahir, stop. This is just beam sitting on top of a column. A beam, a continuous beam that sits on the 3 columns. The answer is no. This is not a continuous beam sits on the 3 columns. This is what we call it a moment frame. And a moment frame, the main difference is the connection between the column and the beam or the girder. This connection here in the moment frame, it means it is a rigid connection. It means both of them, they are rigidly tight, connected together, which will make it be able to resist all the lateral loads. How about if we switch back to here? If we switch back to this connection here, you can see a difference. Just here in this case, the beam sits on top of your column and it's not really a moment connection. It's not rigid connection. You know, if this is to you know, to move laterally, the rotation of them is completely different of the beam and the column. Okay. So the next one is after moment frame. There is a group of structural system that all of them, we call them long span construction. Long span. It means those guys are amazing. They can span for 20, 30, 40, 50 meters, and sometimes hundreds of meters. And so let me give you some names. So some names like something that you know very well, trusses, okay? So concrete trusses are not very popular. So I'm gonna show you here, not really, this is kind of a precast, and I would not call this one truss, and I cannot call it the other name. And if you are really good at statics, like, you know, why cannot we call this as a truss? Look at this picture, please, and just like focus so much. And can you tell me why cannot we call this element a truss? Is there anything missing that's why it's not truss?
Because it's continuous from the top?
Unfortunately, the truss doesn't have to be disconnected. I know in statics they say, okay, it's a called link member, and the link member has to be hinged on each side. But practically, we never do that. It is continuous, and it will still act as a link member as long as we load the nodes. We don't load the member itself. Okay.
Because it's not webbed.
You're very close. But what do you mean webbed?
Like the structure in between the 2 beams is like, it doesn't look like a regular truss. Like, it's only the 2 sides look like it could potentially be webbed, but there seems to be posts in the middle.
There's no gussets.
That's concrete. There's no gusset at all. But by the way, sorry, I'm sorry. Like, I'm sorry if I just laugh, but I'm not really making fun of you of any means. Thank you so much for contribution. So you know. Okay, can I give you an incentive? If you answer this question, why we cannot call this one as this one piece as a truss, I will give you 5% extra on your next assignment. Does it help?
It's currently shared load.
Does it help?
But that your incentive isn't making me any smarter.
How about 10%?
But I still don't know.
Because it doesn't have a 0 member force?
Can you please explain a little bit more? Maybe you're gonna say it's right. Let me show it you one more time. What do you mean it doesn't have a 0 member force?
I don't know. I
Okay,
just know
okay.
trusses
Trust-
have
a
zero.
Trust has to have
First.
2-member force only, no?
No. Okay,
No?
guys, look at this. Okay, I'll answer. I'll give myself 10%. Okay.
I should get half your incentive
Can I?
because I sort of answered right.
No, not really, my friend. No.
So
No negotiation.
No negotiation. Yeah. Okay, let me give you the answer. Okay, I'm gonna turn off my sharing, and then could you please look at my picture? Okay, guys, look at this. So those are my 4 fingers. Okay, and you can see if I do those, you can see my 4 fingers. Think about them as link members, Okay, and you can see my 4 fingers. They simply can move. So this is unstable. Okay, so this is unstable. What makes this system stable? How can I make this stable?
You have to make it connection.
No, you have to add a 3rd member here, another 5th member that splits those into triangles. Okay, if you connect between those 2 points by let's say this. Okay, and so what happens in this case? What happens? The
Stable.
system becomes statically stable. Otherwise, if I remove this, okay, you can see I can simply change the shape. Okay, so let's watch back. Let's watch back to my desktop, and okay, guys, what's missing here is simply the diagonals, and simply the diagonal is what turns your element into a stable system and turn it into a truss. Okay, we can still make it stable. However, we have to make this connection between the column and the beam as a rigid connection. It doesn't allow rotation. Remember, in the truss, what's the assumption? The assumption here is that this is a beam connection. It means it's free to rotate. Okay. So guys, again, the answer is why this whole thing is not a truss. It has to contain an element just like this one, which is diagonal, and this one in all the bays. And if not, then it still can work. But again, we have to make sure that our design make sure that this connection between the verticals and the chord, it is rigid connection, doesn't allow rotation. This is how can we make it a rigid connection. But it has different name called Verndyl. So that's why in my title there, I called it trusses / Verndyl, because it's not really, so from here to there, it's Verndyl. This part here, it's Verndyl. However, this last bay from each end, it is a truss. You guys know what does it mean, truss, huh? The truss, it means all those bays, they must have a diagonal. The diagonal is the secret, okay? Now, whether it's a truss or Verndyl, those they can span for very long spans. And you know what? Like you have seen so many trusses, I guess. Like, you know, I don't have a truss picture here because semi-concrete trusses is not very common. Is very hard to build. Probably it has to be precast. And Verndyl also is not very common. I can show you a picture of a Verndyl, which is from SAIT, which is not really concrete. I'll show you here. Do you guys remember this picture on the right? Have you been to this place before? The picture on the right?
Yes.
So this picture is in Stalingrad. Would you agree? The north side of Stalingrad, where you exit. Okay, do you see in those vertical elements? So you can see where I'm pointing right now, there is a vertical structure on each side. And I'm asking you, what do you think? Can we call this truss? Can we call this thing a truss that holds the front of the glass?
no.
No, you can't. And the reason why we can't, can I get it? Can I hear why we cannot call this a truss?
Diagonal is missing.
Exactly. You can see there is no diagonal from top to bottom. And that's why, how can we make it stable? How can we make it stable? Look at my finger. There's only one way, which is the connection between those horizontal and vertical member. It has to be a moment connection, connection that can resist rotation. Okay. By the way, also, this is very rare. Like, look at this. Only You know, I went on the city for so many places, and to be honest, I don't see those anywhere except for those two places. One in Sate, in the Stangrad building, the north entrance, and if you go to the downtown, I have been walking through the plus 15 one time, and I came across this Vrandile, and I'm crazy about structure. So right away, I took my cell phone and I took this picture on the left. It's I think somewhere east of the TD Square on the plus 15. Okay. Anyway, so again, trusses, Vrandile, beams, moment frames. Guess what? Anyone can or knows what's the name of this structure? I know you guys have the file, but let's be honest, okay? Does anyone in this class know the name or the structural system in this bridge? Okay, no one? No one knows the word arch? Arch? Okay, so the arch is one of the fantastic, and I can tell you one of the oldest structural system that has been ever invented, even I think before BC. Okay, BC. Okay, so I think the Romans and the Egyptians, they used the arches to make windows. It's very, very nice structure, and it turns all your internal forces into compression. So this arch mainly doesn't bend. Just like the truss only has either compression or the tension as long as you load the nodes. If you load the load on the member, then you get bending moment. But if you load the truss only on the nodes, then you get only internal forces like axial, compression, and tension. The truss is the same. If when you load the truss, then all the forces is in compression, no bending moment. And actually, most of our material, they love compression. If you have some bending, then it creates a problem. Okay, so that's why the arch is very efficient and it can span for very long distance. I think that's what I wanted to say about the structural system. Please, when you study this document, just read, that we have simple beam, continuous beam, we have moment frame, and also we have long span, which could be truss, arch, Vrandile. And by the way, so we have cables. So the cable and the suspension cable is also another one, but I didn't include here. It's kind of very complicated. I didn't include here. Okay, so let's move on. So, and please take your time and look through the picture. So I provided some picture to illustrate the meaning of simple beam or continuous beam, the shear walls, like the elevator wells and staircases, and how those are connected. Look at this structure here. At the end of the day, everything has to go and connect itself to the shear wall. Okay. Moment frames, combination between truss and Vrandiles, and then a couple of pictures for the arches. The arches can be this way or it can be this way, and there is a difference, right? So look at this. So if you have a car here, the car will simply send the load to the slab. The slab will send the load to the columns. The column will put some point load on the arch, and the arch will simply bridge the whole thing and give here reaction on this side and reaction on this side. Okay, same thing here. On this arch, you can see if you have a load here on the slab, those columns will work as hangers. So the hanger, they will hang this slab off the arch, adding here point loads on the arch, and the arch simply will take all the loads and put some reaction here on this pier and this pier as well. Okay. Finally, there are a couple of Vrandile. When this Vrandile, it's available in Sate and available somewhere in the downtown. Okie dokie. Next is after we pick the statical system or the structural system, and we have the loads ready, like live load, dead load, seismic load, and so on. What is next? So the next step is here. Look at the name. The name is structural analysis, which means how much is my bending moment, how much is my shear force, how much is my axial force. And you guys learn a little bit about this one. So last year in statics, you learned about those how to find the bending moment for simple beam, how to find the axial force, and you had this last year. And again this year, next class I'm going to go through and review with you guys how to find the bending moment, because simply it's very important for my class. However, in addition to reminding you the manual methods, I'm going to give you 2 hours, probably 3 hours, whatever it takes from us to train you on software called SAFe. And I'm providing here in this document a few snapshots. You can see here, this snapshot is from SAFe. It's analysis for a slab, flat slab with some edge beams and some columns. The SAFe is able to use all the loads, use finite element model to find the bending moment. You can see here there's a kind of a contour map, like you see blue, green, light blue. So what are those colors? Of course, if you have a bigger picture, you will see what do they mean. Here on the right side here, there is a legend tells you, for example, if you have a blue, it means your bending moment is this range. And if you have green, your bending moment is less and it's this range, okay? So we use SAFe to find the bending moments because simply the next step is to design the slabs and the beams and the columns. I provide also in my document here a couple of more examples because this one is, you guys are very familiar with this one. Because what do we call this? What do we call this structural system? Any help?
Truss.
Truss. Thank you so much. Look at all the triangles. 1, 2, 3, 4, 5, 6 triangles. Because simply the triangle is the only shape that can maintain its shape with a number of sides of 3. If you have 4, look at this. If you have 4, look at your fingers. If you have 4, simply you can move anywhere. But as soon as you add the diagonal, simply it will stop it from movement. Okay. So what you see is a truss, and you can see the SAFe can do the analysis. The type of loading here is a uniform load. So we load in red. In red, we have here a uniform load going on the top chord. Okay, question for 5% of next assignment. Okay, I have a question for you for 5% of the next assignment. But the way we do it, please, the way we do it has to be organized. So I'm going to ask my question. Hold on your answer. Hold on the answer. And you show your hands. I'm going to call your name, and then you turn on your mic and speak out. Okay. So one more time, this is a truss. The loading is a uniform load going on the top chord. What you see here in green, or sort of a green, those are the axial force, like the compression and tension. Now, here is my question. Do you think this truss will have bending moment? Okay, and so that's first part of the question. And if it has bending moment, which members they will have the bending moment and why? Now I have to turn it back to my MS Teams, and let's see. Okay, I guess I don't know if the Microsoft team meeting does it order, but I'm gonna go with Hamid because he's on top of my list. Okay, so Hamid, please turn on your mic, and
can you go back to the picture, please?
I will.
It does have a bending moment, and which members will have the bending moment is the top chord.
Why?
Because it's acting in a downward force, like in a compression force.
Okay, so thank you so much. Your answer is correct, but the last part is not correct. So I'm going to assign you probably 3 marks. Please take a note, and you will maybe I'll take a note. So I'm gonna put here next to your name, Hamid, is +3 marks. But still, I need somebody else to tell me. So the last part is not correct. Why the top chord will get some bending? Not because it has a downside loads. Next is, can I get Marin? Marin?
Hi, Tahir. Can I see
Hello.
the diagram?
Oh, for sure.
I think it does have bending moment, and like this picture shows 1.4.
Actually, like my diagram, the green one doesn't show any bending moment. I'm just showing only the axial force. But my
Yeah,
question is regarding a diagram that I'm not showing. I'm not showing.
Then what is that red color?
The red color is the loading. The loading is a uniform load with a value of 1.426 kilonewton per meter. That's the value of the load.
Oh, okay.
Do you
Then
still have the answer?
I thought that's the bending moment. Then I'm sorry. Then I don't know.
No. You don't have to be sorry. You don't have to be sorry. Thank you so much for contribution. I'll go then with the next person. So Martin Garcia.
Hey, Tahir. I think that there will be bending moments along every single piece of truss except ones that are directly vertical. So along the bottom chord and then the diagonal chords in the middle as well. The reason for that is that the force is applied along the y-axis, so it's not going to apply a bending moment in the vertical chords, but it will to any of them that have a direction that's not 100% vertical.
The answer is unfortunately not correct. Not all the members, they will have a bending moment. There's only a few of them, they will have a bending moment, and for a good reason. Okay, so but anyway, thank you so much for your contribution. Thank you so much. Next is I want to get Brody.
It's gonna have a bending moment along the top chords, and I think that's because there's a distributed load across it. It's not just point loaded in one spot.
You got my 5. Thank you. So let me mark this on my. So that's Brody. Thank you so much, Brody. So guys, I think I answered this in the discussion, but some of you probably not really paying attention. The truss. If you load the nodes where the members connects only, all your truss members will have axial force only. Because the top chord is loaded along the top chord members with a uniform load, that's why the top chord will have compression in addition to bending moment. Hopefully this does make sense for you. Okay. So anyway, this is something just, you know what, don't be scared, don't be afraid. You know, there would be hundreds, lots of marks in my class. I will probably every class I will give, you know, fair 5, 10, 20. I don't mind. You don't come from my salary, so I don't mind. Okay. So if you don't get any 5% this time, I assure you that you will get some time. Next is, just I was trying to show you some samples of what SAFI can do for us. It can do even more complicated analysis. This is a DOM where simply, or DOM, it can do the analysis and simply it can find for you the bending moment on this DOM. Okay. Okay, guys, we're very close to end. So now I'm gonna talk about 10 minutes, and what you will hear in the next 10 minutes, please don't consider it as rushed, but because simply this is the core of our design. So if you don't get it today, now, I bet you will get it, because that's what we will say probably every class. Okay, so structural design. What do we mean by structural design? As I said before, we go ahead and make sure we pick one member, or we reinforce the member in a way that it's capable of handling two states. The first state is called ultimate limit state. And look at the name, ultimate. And the word ultimate, it means the final stage of the life of this member, when this member is about to collapse or fail. Okay? So in this state, we're talking about safety. We're talking about member capacity. We're talking about building overturning, about sliding, about fatigue. Those are ultimate state before the member fails. And we have to make sure that the member will not fail. So that's why BART, when we look at our design, we look at this point of life of the member, we make sure that member has enough capacity to resist the loads. early in my class today, I said, no, this is not only the only aspect of our member. It's not only about failure. It's about performance. It's about every day. What if I design one beam and this beam, yes, is strong, is not gonna fail or fall to the ground. However, when I apply my load, it has 100 millimeter deflection, 100 millimeter. What do you think? Would you go under a roof that you can visually and the deflection is visible to you, or you will feel unsafe? What do you think?
Feel unsafe.
Completely unsafe, and you will never do it. You'll never do it. Okay. I'll tell you something. I myself was at one point of my life on a bridge. I was testing for deformation, and simply the bridge is kind of the back and forward direction. They are kind of separate, and simply I stand on one side, and the loading, all the trucks, they were going on the other side, and you can see 100 millimeter of deflection. The good thing is we typically don't stop on bridges. We just move on the bridge, and because we're moving, we don't feel the deflection. But if you were to sit on the bridge and the bridge deflects too much, you will feel scared when this happens. So deflection, vibration is something we, as engineer and designer, we have to think about it. And by the way, deflection will happen every day, not happening only when the structure is about to fail. And that's why from today, I want you to take the two words, ULS, ultimate limit state, and then SL, which is serviceability limit state. What are those? Those are the states which the engineer and the designer have to take care and make sure that the member will perform well under both. Sometimes the engineer or the designer will focus only in one. Unfortunately, some designer will do that. Will look only at the ultimate limit state and do a good job there and make sure the member is not failing. However, they totally forget about the serviceability limit state, which means the performance of this member sucks, like vibrates too much or deflect too much. And this is crazy and sometimes can yield to also problem. I can tell you sometimes in downtown when they make a high-rise building and the engineer will go ahead and they choose the thickness of the slab. Some engineers, they don't pay attention and they choose very thin slab and the slab will deflect too much. What do you think? If the slab deflects too much, what's serious about it? What's the problem? Any idea of what's the problem of deflection? If you have a condo in downtown, those fancy condos, and simply the slab deflects too much, in this case,
it would break.
Overstress.
To be honest, stress is out of the business right now because stress, this is ultimate limit state. Okay, my question is, if it deflects so much in a condo building, what problem does it cause to the structure if it deflects too much?
Could there possibly be pipes bursting? Like water pipes and sewer pipes bursting if it deflects?
What's your name, sir?
Nick.
Okay, I'm gonna write it here. Probably you were not on my list.
It's that's my nickname. It's Nicholas.
Okay, so Nico, I'm gonna give you a mark because simply yes, some of the pipes, they are connected to the floor, and sometimes the pipes will crack. Anybody wants to get another 1%? What else can cause a problem if the slab or the floor deflects so much?
Settlement.
Typically, settlement we refer to the whole structure will go down into the soil. So I don't want to use the word settlement. I would prefer to use deflection. If you have so much deflection,
the beam is the design of the beam is not enough to carry the dead loads and live loads.
You're also still confused. The beam is still alive, still didn't fall to the ground. Nobody's gonna die. Nobody's gonna die. However, it's about every day. I'm talking about deflection, which is serviceability limit state. When we have so much deflection, how this can affect our daily life. What can cause? We have one example of pipes will crack. What else can go wrong?
Could you get like corrosion in the reinforcements if the moisture barrier is broken through the cracks?
Well, probably you're right. If your building envelope, the deflection is too much, and the building envelope is broken, then yes, you get some ingress and you're in trouble. What's your name, sir? Your name, sir?
Brody.
Huh?
Brody.
Okay, perfect. Thank you so much. 6 marks today. Okay. What else? There's still some stuff. Please try to think.
Doors and windows.
Say it again, sorry.
Doors and windows. They can create cracks and windows will not close properly.
Your name, sir? Your name?
Diego.
Diego. Welcome.
Yeah. Thank you.
So yeah, as Diego said, yeah, windows, if you have so much deflection and there is no allowance for those deflections, maybe the windows will also crack. What else? Okay, probably for the tiles. So guys, I mean, we have plenty of marks in this course, so I'm gonna, maybe for the sake of time, I'm gonna answer. Guys, flooring comes on top of the floor. If you have lots of deflection, flooring will crack. How about partition walls? Partition wall, they go on top and you will see cracks. And by the way, this happens and you will see all the owners will just sue the structural engineer because of the deflection, okay? So anyway, what I want you to take from today is when we do a design, it's a must that we ensure the element will not fail. That's one side of the design, but the other side is it has satisfactory performance in terms of vibration, deflection, and so on, okay? And by the way, so you know, you will hear this in steel. So Corwin soon will tell you ULS and SLS. And so no matter what you do, you make sure you remember whether it's wood, concrete, steel, it has to go and take care of the ULS and SLS. Okay? We're very close to end. So we have 3 minutes. And to be honest, I don't like to rush this part. This part is very important. There is a very simple equation in the middle. By the way, the document is almost done, so we're almost there. But this equation here, you see this equation, which is phi multiplied by r has to be more or equal than alpha multiplied by s. Okay, so this equation is a core equation or symbolic equation that we're gonna use in our design. So I prefer to stop now and probably give you a couple of minutes for question, and then we're gonna proceed on Monday. Okay, guys, time for question. I think I have a moderator, so Brody, you volunteer to do that. There was a discussion, but to be honest, I cannot follow. I'm not sure what does mean shut down or. Oh, that's the bridge. Okay. Okay, guys, any other question for me? Any other question for me? Please read, because I myself put effort to prepare materials for you, because I know the online education, it means you need more support. It's in class, we do it better because we are connected. But if you are on one side, I'm on the other side, I have to make sure that I give you enough material. And this material is not for fun, it's for you to read and give me a feedback if there is, so I can improve it for the best of all of us, okay? Okay, so read the material. The best is if you read it tonight. The best is if you read it tonight. And then if you have anything to correct or to add or to modify, just communicate with me. And please, last note is watch for your email. I'm gonna send you some directions for the breakout groups. Thank you and have a good day.